Now the case 1 is for a system of two particles along a line. Here two particles of masses m1 and m2 are placed at positions A and B, and say these two are separated by a distance r. Now the center of mass of the system of these two particles is at a position C on the line joining the two particles, such that m1 into AC is equal to m2 into BC. The definition of location of center of mass in this context is such that m1 into AC is equal to m2 into BC. If r1 is the distance of center of mass from the particle of mass m1 and r2 is the distance of center of mass from the particle of mass m2, then m1 r1 is equal to m2 r2. So now from the geometry of this figure, we can make two equations. One is just as we have discussed now, m1 r1 equal to m2 r2, and next r1 plus r2 is equal to r, the distance between the two particles. So now by solving these two equations, we can write expressions for r1 and r2 as r1 equal to m2 by m1 plus m2 into r, and r2 equal to m1 by m1 plus m2 into r. Very important, very useful formula these two are. r1, the distance of center of mass from the particle of mass m1, that is r1, is m2 by m1 plus m2 into r, and r2, that is the distance of center of mass from the particle of mass m2, as m1 by m1 plus m2 into r. And this is how we locate the position of center of mass in this case of two particles separated by a distance r. And then let's locate the center of mass in a system of two particles placed along x-axis. Now we are putting the same two particles of masses m1 and m2 along the x-axis of a coordinate system. Here m1 and m2 are located at A and B at distances x1 and x2 respectively from the origin. So x1 is the location of the particle of mass m1 from the origin, and x2 is the location of the particle of mass m2 from the origin. Now again, if we say C is the center of mass, it is located on the line joining the two particles. And now the location of the C is such that from our very definition, m1 into AC must be equal to m2 into BC. So we can write the same expression as m1 into AC is nothing but OC minus OA, and that equal to m2 into OB we can write as, that is BC we can write as BC. We can write as OB minus OC. A simple geometrical relation. Therefore, m1 into here OC is the position coordinate of center of mass denoted by x suffix cm. So we can write the above expression as m1 into xcm, that is OC is xcm, minus x1, OA is x1, is equal to m2 into x2 minus xcm, where xcm is the position coordinate of center of mass. So now by rearranging this expression, we get xcm as m1 x1 plus m2 x2 by m1 plus m2. A very useful beginning. The same context we are going to apply for so many cases later on, just to understand a very simple base level context of location of two particles of masses m1 and m2 on x-axis at positions x1 and x2 respectively from the origin. Now the position coordinate of center of mass OC equal to XCM is equal to m1 x1 plus m2 x2 by m1 plus m2. Now case 3, let us extend the above discussion for a system of n particles along x-axis with the positions x1, x2, x3 so on xn for the particles of masses m1, m2, m3 so on mn. Now the position coordinate of center of mass XCM is equal to m1 x1 plus m2 x2 plus so on plus mn xn by m1 plus m2 plus so on plus mn. And then for a system of n particles in a plane, we have discussed for system of n particles on a line in the previous case. Now the particles are now in a plane, means there will be two position coordinates, x coordinate as well as y coordinate, because we are on a plane. So now the position coordinate of the center of mass in xy system is given by two coordinates xcm and ycm, where xcm equal to, because each particle is with two coordinates, m1 will be the x1 y1, m2 x2 y2, m3 x3 y3 so on mn xn yn. So xcm equal to m1 x1 plus m2 x2 so on plus mn xn by m1 plus m2 so on plus mn, and ycm is m1 y1 plus m2 y2 so on plus mn yn by m1 plus m2 plus so on plus mn. Simply we can write by the sigma notation. XCM is sigma mi xi I equal to 1 to n divided by sigma mi I equal to 1 to n. Similarly YCM sigma mi yi where I equal to 1 to n divided by sigma mi where I equal to 1 to n. Easy to remember and easy to express. And then if the particles are now in space, first case line, next plane, and now particles are in space. So each particle will be with three position coordinates x1, y1, z1. So m1 is with three coordinates. M1 is x1, y1, z1 coordinates. For m2, x2, y2, z2. For m3, x3, y3, z3 so on, plus for mn, xn, yn, zn. Now this time the center of mass will be expressed with the three position coordinates xcm, ycm and zcm. By the same method, xcm is sigma mi xi where I equal to 1 to n divided by sigma mi I equal to 1 to n. And similarly you can practice for ycm and zcm. And then case 6. Now I am going to give you three cases, case 6, case 7 and case 8. All three are very important for our conceptual questions in our entrance examinations. Here case 6, n number of particles, each of mass m are at distances x1 equal to 1, x2 equal to 2, x3 equal to 3 so on, xn equal to n units from the origin on the x-axis. All particles are of same mass, each m, and they are located at distances 1, 2, 3 so on n units from the origin on the x-axis. Now the distance of the center of mass from origin, that means the position coordinate of center of mass from the origin, is from our very base method or base formula. XCM will be equal to m1 x1 plus m2 x2 plus so on plus mn xn by m1 plus m2 plus so on plus mn. Now by using the given data, it will be m into 1 plus m into 2 plus m into 3 so on plus m into n divided by mass of all particles m plus m so on. Like that n terms will be there because there are n particles we say. Now if you take common m, and that here in the numerator and in the denominator will be totally nm because there are n terms, and that m gets cancelled. So in the numerator we left with the sum of the natural numbers 1 plus 2 plus so on plus n divided by, here the denominator we left with n. So what is the sum of natural numbers by formula? N into n plus 1 by 2. Anyhow, m is already cancelled and divided by n. Sum of natural numbers formula n into n plus 1 by 2. And here in this expression we have divided by n, and n also if you cancel, what remains is n plus 1 by 2. So the position coordinate of center of mass from origin, this case is n plus 1 by 2. Very important conclusion. And case 7, this time again n number of particles of masses m, 2m, 3m, so on nm. Previous case all are each is of mass m, but now the masses m, 2m, 3m, so on nm are at distances, again x1 equal to 1, x2 equal to 2, x3 equal to 3, so on, xn equal to n units respectively from the origin on the x-axis. Now the position of center of mass measured from the origin is such that, again same rule, m1x1 plus m2x2 plus so on plus mnxn divided by m1 plus m2 plus m3 so on plus mn. So we substitute the values, m into 1 plus 2m into 2 plus 3m into 3 so on plus nm into n divided by sum of the masses m plus 2m plus 3m so on plus nm. So this time as we cancel m, in the numerator we left with the sum of the squares of the natural numbers, 1 square plus 2 square plus 3 square plus so on plus n square. In the denominator we left with the sum of the natural numbers, 1 plus 2 plus 3 so on plus n. So we substitute the formula, sum of the squares of natural numbers is by formula n into n plus 1 into 2n plus 1 by 6. Sum of the squares of the natural numbers is n into n plus 1 into 2n plus 1 by 6. Sum of natural numbers in the denominator n into n plus 1 by 2. So when we simplify this expression, we left with 2n plus 1 by 3. Look here, 2n plus 1 by 3 is the position coordinate of the center of mass measured from origin. And next case 8. Another interesting question for us. N number of particles of masses m, 2m, 3m, so on nm are at distances at x1 equal to 1, x2 equal to 4, x3 equal to 3, so on, xn equal to n square. Means at distances 1 square, 2 square, 3 square, so on n square. Now this time the particles are also of different masses m, 2m, 3m, so on nm. Now when we use the same rule here, XCM m1 x1 plus m2 x2 so on plus mn xn by m1 plus m2 plus so on plus nm, when we substitute the given data and when we simplify it, we left with a numerator sum of the cubes of the natural numbers and in the denominator sum of natural numbers. 1 plus 1 cube plus 2 cube so on plus n cube divided by 1 plus 2 plus 3 plus so on n. Now the sum of the cubes of the natural numbers is given by the formula n into n plus 1 by 2 whole square. N into n plus 1 by 2 whole square. Sum of the cubes of the natural numbers divided by sum of natural numbers n into n plus 1 by 2. So when we simplify this, we left with n into n plus 1 by 2. So 3 very important cases we have discussed. So you go through all these cases again from your notes also, very useful, very important. And then case 9. This time to write position vector of center of mass. Until now we have discussed position coordinates of center of mass. Now position vector, the line vector joining the origin and the located center of mass, is the position vector of center of mass. the line vector joining the origin and the position of center of mass is the position vector of center of mass. And suppose for n particles, masses m1, m2, m3, so on, mn are located with the position vectors r1 bar, r2 bar, so on, rn bar respectively. In a given coordinate system, n particles with masses m1, m2, m3, so on, mn are located with the position vectors r1 bar, r2 bar, r3 bar, so on, rn bar. Now, the position vector of center of mass denoted by RCM bar, R suffix CM bar, is as RCM bar equal to M1 R1 bar plus M2 R2 bar plus so on Mn Rn bar divided by M1 plus M2 plus so on plus Mn. Observe this. RCM bar is M1 R1 bar plus M2 R2 bar so on plus Mn Rn bar by M1 plus M2 so on plus Mn. Another way we can write as sigma mi ri bar, where I equal to 1 to n divided by sigma mi I equal to 1 to n. Here obviously will be equal to the sum of the masses of all the particles, the denominator. So this is a simple expression to remember easily. And then case 10. This is to locate the position vector of center of mass of a continuous mass distribution. That is in case of a rigid body. A rigid body may be treated as a continuous distribution of mass. The particles of the body then becomes differential mass elements, each of mass dm, and the earlier summation mode now become integration. And here this concept of locating position vector of center of mass in case of a rigid body better we can understand in our numericals. So I have given you enough numericals on this concept. There you can have a complete picture of the location of position vector of center of mass in case of a continuous mass distribution. But anyhow, here let's write the formula what we are going to use there. Here the integrals are evaluated for all mass elements in the object such that xcm is integral of dmx divided by integral of dm, ycm is integral of dmy divided by integral of dm, and zcm is integral of dm z divided by integral of dm. I will explain you about this again in numericals video. And here in case of continuous distribution of mass, to locate the position vector of center of mass, the formula that we use is RCM bar is integral of dm r bar divided by integral of dm. And of course the denominator integral of dm is nothing but total mass of the system.